In this video, I am going to present you the linear parameter estimation through an introductory example. So this is just an introduction to the parameter estimation. First, let us imagine that we have got a system, and this system is denoted by with this black colored block, and the function inside is an f function between the input u and the output y. So we can put some input u to the system, and we can measure the output y, and made a very simple plot on the left. So on the horizontal axis there is the input, and in the perpendicular there is the output. So it's an input-output characteristic which we can set up in this case. Let us imagine that we have got a measured data u1 and the output is y1. So for the second input, the feeding is u2, and the output, the response of the system, is y2, and so on. So for example, this is ui, the index will be I, and this index we are going to use in the future. So this point is a u index I and y index I pair. And the number of this measured data is denoted by n. So we have got n measured input-output data. We are going to set up a model for this. The model here in this block is something. And in this case, and this is why it's an introductory example, the model is very, very simple. It's a linear model with two parameters, p0 and p1. We don't know this value yet. We would like to calculate p0 and p1 somehow to get a linear model. And this linear model looks like this one. This will be the modeled characteristic. So we are going to give the same input to the model, and inside the model there is the equation given by the model which we introduce, and we are going to get y hat. And we would like to get more or less the same as the value of y, but usually there is an error. There is an error, for example here, the difference between the measured data, this is the green point, and the model data, this is given by the red line. So it's an error between the measured and the simulated data. But this error can be positive or negative, so it's very, very useful to take at least the square of this error value, because in this case the error will be always positive and we can find the minimum of it. That's why we are going to define the so-called quadratic error function, and it's a much better, a much clever way than using the individual error e index I. So how to define the quadratic function? It's a half. We are going to speak about it, why we need half. The sum is coming from 1 to n, and we are going to get the square of the errors. So in every measured points we are going to calculate the difference between the measured and the simulated data. This is the error e. We are going to calculate the square of it. We are going to sum all of the individual errors, and we are going to take the half of it. The half is very useful because there is the square in this error function, and later we are going to get the derivative of it, and this 2 is going as a multiplicative 2, and this 2 and this half are going to kill each other. Okay, that's why we use this 1/2, nothing special. So what is the next step, we are going to use this definition here. So the sum is from 1 to n, y index I minus y index I and hat square. So the next step is to put the model into y hat. So this is what I am going to copy here. So the sum is from 1 to n, y index I minus the model p0 plus p1 and u index I and square. So now this is only valid for this very simple linear model, but I would like to generalize it. That's why we need the next step for the generalization. The half of the error y index I minus, I am going to pull out the inputs like 1 and ui to a row vector. So the value from here, and this is to here, and then I am going to put the model parameters to a column vector, and I am going to get the square of it, of course. So this is more general description like the last one. So, and I am going to use some notation for this. This will be phi index I and the transpose of it, because it's a row vector. The second is a p hat vector. It's a column vector. So the phi I is going to collect the input data, which is using the values of u index I, and the unknown parameters are collected to the vector p hat. So in this case, the quadratic error function, in the general way, we can obtain the following: 1 over 2, the sum from 1 to n, y index I minus phi I transpose and p hat square. And this is what we are going to work on in the future lectures. So there are two arguments of this quadratic function, n, because the error is depending on the number of the measured data, and of course the parameters. And we are going to take the derivative of this quadratic error function by the parameter vector, of course, because we would like to minimize this error somehow. And this technique has a name. The name is the least square method, or the LS method. Okay, LS estimation is the other name for that. And the goal of this least square method is to minimize the quadratic error function, which will be presented in the next lectures.